Asynchronous counters. We have seen the introduction to counters in our previous tutorial, and now we're here to discuss asynchronous counters. As we discussed earlier, asynchronous counter is one in which each flip-flop is triggered by the output of the previous flip-flop, which limits the speed of operation. Asynchronous counters are also called ripple counters. These counters are easier to design and are constructed using minimum hardware. Now let's discuss a few examples of asynchronous counters. At first, we'll start with the 2-bit asynchronous counter. A 2-bit asynchronous counter circuit is given. We have connected the external clock only to the clock input of the first flip-flop, that is FF0. Here we have given a bubble at the clock, which indicates that output changes its state during the negative edge or falling edge of the clock pulse. So FF0 changes state at the falling edge of each clock pulse, but FF1 changes only during the falling edge of the Q output of FF0. Because of the inherent propagation delay through a flip-flop, we know that the transition of the input clock pulse and a transition of the Q output of FF0 can never occur at exactly the same time. Therefore, the flip-flops cannot be triggered simultaneously, producing an asynchronous operation. You may wonder, by seeing this timing diagram in which the transitions of Q0, Q1, and clock are shown as simultaneous, even though this is an asynchronous counter. But actually there is some small delay between the clock, Q0, and Q1 transitions. Usually, all the clear inputs are connected together, so that a single pulse can clear all the flip-flops before counting starts. The clock pulse, which we have given externally, is fed into FF0, and is rippled or moved through the other counters after some propagation delays, like a ripple on the water, hence the name ripple counter. The 2-bit ripple counter circuit, which we discussed now, has 4 states, each one corresponding to a count value. Similarly, a counter with n flip-flops can have 2 to the power n states. The number of states in a counter is known as its mod, or modulo number. Thus, a 2-bit counter is a mod 4 counter. We'll discuss these mod counters in our upcoming tutorials. Now, let's discuss asynchronous up counter. This is a very simple basic counter. For up counters, the transition will be from high to low. Here we have the circuit diagram. Waveforms and table are given for your better understanding. QA output changes for every negative transition of clock pulse. QB output changes whenever there is a transition from logic 1 to logic 0 in QA. QC output changes whenever there is a transition from logic 1 to logic 0 in QB. Now, let's discuss the asynchronous down counter. This is very similar to the up counter. The only difference is that for the down counter, the transition will be from low to high. Here is the circuit diagram for you. The waveforms and the table are here. QA output changes for every positive transition of clock pulse. QB output changes whenever there is a transition from logic 0 to logic 1 in QA. QC output changes whenever there is a transition from logic 0 to logic 1 in QB. Here we have a note to remember. An up counter using n flip-flops counts upward from a minimum count, that is from 0 to 2 to the power n minus 1. And a down counter using n flip-flops counts downward from a maximum of 2 to the power n minus 1 to 0. Now, let's discuss the asynchronous up-down counter. In certain applications, we may need a counter that must be able to count both upwards and downwards. Now we're going to discuss such a counter that counts both up as well as down. The circuit given is a 3-bit up-down counter. It counts up or down depending on the status of the control signals up and down. When we give the control input up as 1 and down as 0, the NAND network between FF0 and FF1 will give the non-inverted output Q of FF0 as the clock input for FF1. Similarly, Q of FF1 will be given through the other NAND network into the clock input of FF2. Thus, the counter will count up. When we give the control input up as 0 and down as 1, the inverted outputs of FF0 and FF1, that is Q bar and Q1 bar, are given as the clock inputs for FF1 and FF2 respectively. If the flip-flops are originally reset to zeros, then the counter will count downwards as input pulses are applied. Here is the table for you, which gives you a clear understanding of how this counter counts up as well as down. From the circuit, it is clear that an asynchronous up-down counter is slower than an up counter or a down counter because of the additional propagation delay introduced by the NAND networks. I hope you're clear about these up-down counters. Now we will discuss the asynchronous decade counter. The binary counters which we have discussed so far have 2 to the power n states. But counters with states less than this number are also possible. They are designed to have the number of states in their sequences which are called truncated or reduced sequences. These sequences are achieved by forcing the counter to recycle before going through all of its normal states. A common modulus for counters with truncated sequences is 10. A counter with 10 states in its sequence is called a decade counter. The circuit given here is an implementation of the decade counter. Once the counter counts to 10, that is 1010, all the flip-flops are being cleared. Notice that only Q1 and Q3 are used to decode the count of 10. This is called partial decoding, as none of the other states from 0 to 9 have both Q1 and Q3 high at the same time. The sequence of the decade counter is given in this table. Now I hope you all understand these asynchronous counters and the various types of asynchronous counters which we came across in this tutorial. So now we'll move on to the next lesson, which deals with synchronous counters.